Tonight, we are going to embark on a voyage toward the closest stellar system that exists outside our own cosmic doorstep, Alpha Centauri. It hangs quietly there in the southern sky, roughly 25 trillion miles distant from where you are sitting right now. Over the course of this video, we are going to work out precisely what a voyage to that destination would demand. Not merely the mathematics of it, not just the engineering puzzles, but the unvarnished reality of what an undertaking like that would actually mean for any human being who dared to attempt it. Because here is the truth that almost no one ever genuinely confronts. Reaching Alpha Centauri is not simply challenging. It is not merely a question of constructing a larger booster or biding our time until the technology catches up. It is something exponentially more extreme than any of that. The voyage to our closest stellar neighbor would rank among the most harrowing ordeals ever conceived in human history. And by the time this video ends, you are going to understand in precise detail exactly why that is the case. Before we dive in, if you are someone who finds the vast reaches of space as captivating as I do, take a brief moment to hit the like button or subscribe to the channel. It is a small gesture, but it helps this work reach more curious minds like your own. Now, let us begin. Let's start with what you believe you already understand about Alpha Centauri. You have probably heard at some point that it is the closest star to our own sun. That is not strictly accurate, but for most conversational purposes it is close enough. Alpha Centauri is, in reality, a triple star system. 3 suns bound to one another by gravitational attraction, sitting roughly 4.37 light-years away from us. That works out to approximately 25.6 trillion miles, or somewhere in the neighborhood of 41 trillion kilometers. On a cosmic scale, this is essentially the house right next door. The 3 stars carry the designations Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri A and B are both sun-like stars that circle around one another in a graceful dance, while Proxima Centauri is a diminutive red dwarf that wheels around the pair at a significantly greater remove. Proxima is actually the nearest of the 3 to us, sitting at roughly 4.24 light-years out, which explains the name Proxima from the Latin, simply meaning nearest. Back in 2016, astronomers announced something extraordinary. They had detected a planet in orbit around Proxima Centauri. They christened it Proxima Centauri B, and this world turned out to be approximately the same size as Earth, orbiting inside what might plausibly be the habitable zone, the band around a star where temperatures could allow liquid water to pool on a planet's surface. That single discovery transformed Alpha Centauri from an abstract astronomical curiosity into something far more compelling as a target for interstellar exploration. We might not simply be visiting another star. We might be visiting a world where life itself could potentially have taken hold. But before we allow ourselves to get swept up by visions of extraterrestrial biology, we have to grapple with the brutal reality of the journey itself. 4.24 light-years does not, on its face, sound like such an enormous number. A light-year is nothing more than the distance that light can cover in a single year of travel. And light is the undisputed speed king of the entire universe, tearing through space at roughly 186,000 miles every second, or about 300,000 kilometers per second. The photons streaming from Proxima Centauri need 4.24 years to complete their journey to Earth. That means when you gaze at Proxima Centauri through a telescope, you are looking at it as it appeared 4.24 years in the past. The light abandoned that star more than 4 years before it finally struck your retina. So if light can accomplish the crossing in 4.24 years, how long would the same trip take us? This is where the situation becomes deeply uncomfortable. The fastest vehicle that human beings have ever constructed is the Parker Solar Probe, which was launched back in 2018 with a mission to study our own sun. At its absolute peak velocity, the Parker Solar Probe reaches a staggering 430,000 miles per hour, or about 692,000 kilometers per hour. By any human yardstick, that is an almost unimaginable speed. Moving at that velocity, you could cross the continental United States, from New York to Los Angeles, in somewhere around 6 seconds flat. But measured against the cosmic scale, it is agonizingly, painfully slow. If the Parker Solar Probe were aimed at Proxima Centauri, which of course it is not, it would require approximately 600–700 years to arrive. Let that figure sink in for a moment. 600 700 years. The entirety of recorded human history spans only about 5,000 years. Our most advanced spacecraft would take longer to reach the nearest star than our entire civilization has existed. And that is before you even consider that the spacecraft cannot actually maintain such a speed for any extended period. The Parker Solar Probe reaches its incredible velocity by allowing itself to plunge toward the Sun and picking up boost after boost from gravity assists. Out in the empty reaches of interstellar space, far from any massive body that could offer a gravitational kick, it would begin to slow. You would require continuous propulsion just to hold your speed, and propulsion demands fuel, and fuel is heavy. And hauling that heavy fuel requires additional fuel to accelerate the mass of the fuel itself. And that is how you slam headfirst into one of the most unforgiving problems in all of rocket science. So let's say we want to get there quicker. What would that require? The conventional rockets we rely on today, even our finest chemical engines, cannot pull it off. They are simply far too slow. To complete the crossing within a single human lifetime, you would need to travel at a meaningful fraction of the speed of light itself. And nothing we have constructed, nothing we have even sketched on paper in detail, comes anywhere close to that capability. There are, however, theoretical propulsion concepts that might conceivably work. Nuclear pulse propulsion, where you detonate atomic weapons behind your spacecraft and ride the resulting shockwave. Fusion drives, which fuse hydrogen atoms together to release torrents of energy. Antimatter engines, which annihilate matter with antimatter to extract every ounce of available thrust. Ion drives, which hurl charged particles out the back at blistering velocities. Solar sails, pushed along by the pressure of starlight, or the concentrated beam of a powerful laser. Every one of these concepts carries its own set of complications. Nuclear pulse propulsion received serious study back in the late 1950s and the 1960s under the banner of Project Orion. The concept was elegantly simple on paper. You drop atomic bombs out the rear of your spacecraft, detonate them, and absorb the blast using a colossal shock absorber plate. Computer simulations indicated that this could actually function, potentially accelerating a ship to several % of the speed of light. But there were some rather obvious complications. You would need literal thousands of nuclear weapons. The radiation environment would be catastrophic. The engineering obstacles were gargantuan. And launching a craft of that description from the surface of our planet would be politically unthinkable and practically impossible. Fusion drives appear much more attractive. Our sun runs on fusion, forcing hydrogen atoms together into helium and releasing tremendous energy in the process. If we could manage to harness that reaction inside a controlled chamber, we could theoretically construct an engine of extraordinary efficiency. The fuel source, hydrogen, happens to be the single most abundant element in the cosmos. But we have yet to achieve controlled fusion, not in a functioning power plant on Earth, and most certainly not in a compact, lightweight form suitable for bolting onto a spacecraft. Scientists have been pursuing fusion for more than 7 decades now, and we are still not there. Even the most optimistic forecasts suggest we are still decades away from a practical fusion power plant, let alone a fusion rocket engine. Antimatter engines are even further out in the realm of speculation. When ordinary matter and antimatter encounter one another, they annihilate completely, converting every bit of their mass directly into pure energy. According to Einstein's famous equation, E=mc², this is the most efficient release of energy physically possible. A minuscule quantity of antimatter could, in principle, deliver enormous propulsive force. The trouble is producing and containing it. We can manufacture the stuff in particle accelerators, but only in microscopic trace quantities. The entire cumulative amount of antimatter that humanity has ever produced on Earth would struggle to keep a single light bulb burning for a handful of minutes. Scaling that up to the kilograms or tons you would need for an interstellar voyage is nowhere within shouting distance of our current technological capabilities. And even if, by some miracle, you had the antimatter in hand, storing it is very nearly impossible. It cannot come into contact with any ordinary matter whatsoever, or it will instantly annihilate. You would need magnetic containment systems capable of suspending the antimatter flawlessly for years or even decades without a single failure. One malfunction, and your fuel supply detonates with more raw energy than a nuclear weapon. Ion drives, in contrast, are actual operational technology. We have already deployed them on spacecraft like Dawn and Deep Space One. They operate by ionizing a gas, typically xenon, and then accelerating the resulting ions through electric fields. The thrust produced is minuscule, but because the drives are so efficient, they can run for years on end, gradually building up velocity. The trouble is that gradual acceleration takes gradual amounts of time. Ion drives are magnificent for missions within the boundaries of our own solar system, but for interstellar crossings you would need to run them continuously for decades on end just to reach a fraction of 1% of light speed, and you would need enormous amounts of electrical power, probably from nuclear reactors, which adds mass, which demands more thrust, which requires more fuel in turn. Solar sails are beautifully elegant in concept. Light itself carries momentum. When photons emitted by the sun strike a reflective surface, they transfer that momentum, producing a tiny outward nudge. If you built a sail large enough, lightweight enough, and sufficiently reflective, the sun itself could press it up to significant speeds. The Japanese Ichiro spacecraft demonstrated this very technology back in 2010. A solar sail could, in theory, accelerate indefinitely, so long as there is light still falling upon it. The difficulty is that light pressure is almost vanishingly weak. To achieve any usable acceleration, you need a sail that is absolutely enormous, potentially square kilometers in total area, but also nearly massless, weighing only a few grams per square meter. Fabricating such a structure represents a monumental engineering feat, and even if you manage to build it, the sun's light weakens at a dramatic rate as you recede from it. By the time you have passed beyond the orbit of Mars, the light pressure has grown so feeble that acceleration drops to negligible levels. One proposed workaround is to employ a ground-based or orbital laser array to beam concentrated photons at the sail. The Breakthrough Starshot initiative, announced back in 2016, proposes precisely this arrangement. The plan is to construct a massive laser installation on Earth or in Earth orbit and use it to drive a minuscule spacecraft equipped with a feather-light sail. The craft itself would be roughly the size of a microchip, weighing only a gram or thereabouts, with a sail spanning just a few meters across. The laser would illuminate the sail for only a few minutes, accelerating the probe to approximately 20% of the speed of light. At that velocity, it could reach Alpha Centauri in roughly 20 years. The idea sounds tantalizing, but the obstacles are substantial. First, the laser array would need to be unbelievably powerful, probably on the order of gigawatts of output. That is the total output of an industrial-scale power plant. And every bit of that energy would need to be focused with surgical precision onto a tiny sail that is already sprinting away from Earth at thousands of kilometers per second. The precision required is genuinely staggering, a microscopic misalignment, and the beam misses the sail entirely. Second, the craft would be so small that it simply could not carry much in the way of scientific instrumentation. A handful of cameras, perhaps some basic sensors, but nothing truly sophisticated. It could not carry enough electrical power to transmit significant data back home, at least not at any reasonable rate. You might capture a few images, a tiny handful of measurements, and that would be the sum total. Third, once the spacecraft is accelerating, there is no mechanism to slow it down. It would scream past Proxima Centauri at 20% of light speed, giving it only hours, maybe even less, to observe and relay data before it is gone, tumbling forever into the depths of space. And fourth, even at 20% of light speed, communication presents a daunting problem. The spacecraft would be more than 4 light-years distant. Any signal it fired back would require 4 years just to reach Earth. By the time the data arrives, the craft itself would be long since departed. And if anything went wrong out there, we would have absolutely no way to repair it. So even the most optimistic blueprints for interstellar travel involve severe compromises. But let us pretend, for argument's sake, that we resolve every one of these obstacles. Let us say we develop a propulsion system that can accelerate a crewed spacecraft to 10% of the speed of light. That remains 40 times faster than our fastest existing spacecraft, but it sits within the realm of theoretical possibility. At 10% light speed, the journey to Proxima Centauri would require approximately 42 years. That is the transit time one way. Now we have to contemplate what that figure means for the crew. 42 years represents a substantial chunk of a human lifespan. If you departed at the age of 30, you would arrive at 72. You would spend the entirety of your adult life trapped aboard a spacecraft, never setting foot on solid ground, never drawing a breath of fresh outdoor air, never again laying eyes on a natural horizon. And that assumes that every single thing goes absolutely perfectly. Let us talk about what daily existence would actually be like on such a voyage. First, the spacecraft would need to be enormous, large enough to sustain a crew for several decades. You would require living quarters, workstations, life support infrastructure, food and water reserves, medical facilities, exercise apparatus, and almost certainly recreational zones to preserve what mental stability the crew could manage to hold on to. The crew would need to be entirely self-reliant. There would be no resupply missions following behind them. No help would be arriving from Earth if some critical system failed. Everything the crew required for 42 years of existence would have to be loaded aboard from the moment of launch, or they would have to manufacture it themselves from raw materials along the way. That means the spacecraft would need to be enormous, probably several hundred meters in total length, possibly even more than that. It would need to function as a self-contained biosphere, a tiny floating fragment of Earth drifting through the emptiness. The question of crew size is critical and deeply complex. Too few people, and you encounter genetic problems if you are planning a multi-generational voyage, or you simply do not have the depth of expertise to handle every conceivable emergency. Too many people, and you need exponentially more space, more food, more water, more breathable air, and the spacecraft becomes impossibly massive to accelerate. Most studies suggest a minimum crew size of several hundred to a full 1,000 people for a multi-generational mission, though a shorter voyage might be viable with fewer. For a 42-year crossing, you could potentially manage with somewhere between 50 and 100 individuals, provided they are all experts across critical fields like medicine, engineering, biology, and psychology. These individuals would have to coexist and collaborate in an extremely confined environment for more than 4 straight decades with no possibility of ever stepping outside. The psychological burden would be almost beyond description. Human beings evolved to inhabit wide-open environments filled with variety and novelty. Being confined inside a metal box for decades, looking at the same faces, treading the same corridors, consuming the same recycled food, it would test the sanity of anyone ever born. Research on isolated environments like Antarctic research bases, submarine crews, and residents of the International Space Station provides us with at least some inkling of what to expect. Even in these comparatively brief missions lasting a handful of months or a year or two, participants consistently experience depression, anxiety, interpersonal friction, and measurable declines in cognitive performance. Now multiply that stress by decades. You would need extraordinarily careful crew selection, brutal psychological screening protocols, robust social architecture, and almost certainly professional counselors embedded as part of the crew. Even then, conflicts would inevitably erupt. Romantic entanglements, jealousies, personality clashes, political disagreements, every variety of the usual human drama, but with no escape hatch, no way to physically remove yourself from the people you are fighting with. In extreme scenarios, you might even see violence, mental collapses, suicides. Mission planners would need to prepare for these possibilities, which is a rather grim line of mathematics. Then there is the physical environment to contend with. The spacecraft would be in freefall for the overwhelming majority of the journey. Weightlessness causes bone density loss, muscle wasting, fluid redistribution, vision problems, and immune system disruption. Astronauts aboard the International Space Station exercise for hours every single day just to counter these effects. And even so, they experience significant physiological decline after a mere 6 months. For a 42-year voyage, you would need artificial gravity. The most practical mechanism for generating artificial gravity is through rotation. You spin the spacecraft, and centrifugal force pushes everything outward toward the outer hull, mimicking the sensation of gravity. But this approach introduces its own engineering headaches. The spacecraft would need to be designed as a rotating cylinder or a torus shape. The rotation rate has to be tuned precisely. Too slow, and the artificial gravity is too weak to be useful. Too fast, and the Coriolis effect becomes a serious problem. The Coriolis effect is what occurs when you move around within a rotating frame of reference. If you walk perpendicular to the direction of spin, you feel a sideways force acting on your body. This can cause nausea and disorientation. Studies suggest that you need a rotation radius of at least 100 meters to keep Coriolis effects within a tolerable range, which means the spacecraft needs to be large, and we are talking very, very large. Power generation represents another critical concern. You would need colossal amounts of electrical power for life support, for propulsion, for lighting, for computers, for communication. For every conceivable system, solar panels would be useless. Once you are beyond the orbit of Mars, sunlight is already too weak to be meaningful. By the time you have traveled even a fraction of the way toward Alpha Centauri, the Sun is just another star, providing essentially negligible energy. You would need nuclear reactors. Probably multiple reactors, for redundancy in case one fails. These reactors would need to operate continuously for decades without any maintenance beyond what the crew could perform on their own. The fuel would need to last for the entire voyage, or else you would need to transport spare fuel rods, which adds yet more mass. And nuclear reactors generate heat as a byproduct. In space, getting rid of waste heat turns out to be surprisingly difficult. Because there is no surrounding air to carry the heat away, you need radiators. Large panels that shed heat by emitting it as infrared radiation. The more powerful your reactors, the more radiators you need, and radiators are heavy and vulnerable to damage. Food and water are perhaps the most fundamental challenges of all. You simply cannot pack 42 years' worth of food for 100 people. The sheer mass would be astronomical. You would need a closed-loop life support system. This means recycling absolutely everything. Water from bathing, from urine, from humidity in the air, every drop filtered, purified, and returned to service. The International Space Station already practices this, recycling approximately 93% of its water. You would need to drive that efficiency even higher, closer to 100%, because any loss accumulates catastrophically over decades. Food would have to be grown aboard the spacecraft. You would need hydroponic or aeroponic gardens, cultivating plants under artificial lighting. The plants would also help cycle carbon dioxide back into breathable oxygen, supporting the life support system. But producing enough food for 100 people requires significant volume and energy. The plants need light, water, nutrients, and constant monitoring. Crop failures could be outright catastrophic. You would need backups, seed banks, multiple growing chambers, in case one becomes contaminated or fails outright. Meat would be a genuine luxury, probably limited to laboratory-grown cultures, if available at all. Most of the diet would consist of vegetables, grains, and perhaps fish from aquaculture tanks. Variety would be painfully limited. After a few years, the crew would know every meal by heart. Medical care represents another tremendous concern. People get sick. They get injured. They develop chronic conditions. On Earth, you go to a hospital. On an interstellar spacecraft, you are the hospital. The crew would need at least one physician, probably several, along with a well-stocked medical bay. But what happens when someone needs surgery for appendicitis, a compound fracture, or cancer? The crew would have to handle it with whatever equipment and supplies they brought along. Advanced imaging technology like MRI scanners might not even be available, given the mass and power requirements. Pharmaceutical supplies would be sharply limited. Some medications degrade over time, gradually losing their potency. You would need to manufacture certain drugs on board or transport enormous stockpiles. And what about the slow ravages of aging? If the crew is in their 30s at launch, they will be in their 70s upon arrival. They will experience every single health problem associated with aging. Heart disease, arthritis, dementia, vision loss, hearing loss. Some crew members will not make it to the end of the voyage. That is a statistical certainty for any 42-year journey. The spacecraft would require facilities for dealing with the deceased. Probably some form of burial into space or storage in a dedicated area. It is grim to contemplate, but it is a reality that mission planners would have to confront directly. Now let us discuss the actual dangers of the journey itself. Space is not empty. There is gas, there is dust, and occasionally there are rocks. At ordinary spacecraft speeds, striking a grain of sand is not much of an event. At 10% of light speed, it is like being hit by a bomb. Kinetic energy scales with the square of velocity. Double your velocity, and kinetic energy quadruples. At relativistic speeds approaching the speed of light, kinetic energy climbs to enormous figures. A single speck of dust, maybe a milligram in mass, striking at 10% light speed, carries the kinetic energy of several kilograms of TNT. A small pebble, just a few grams, would hit with the force of a nuclear weapon. The spacecraft would require shielding, heavy, thick shielding at the forward end to absorb or deflect impacts. But shielding adds mass, which makes the spacecraft harder to accelerate, which demands more fuel or a more powerful engine. You might also employ magnetic fields to deflect charged particles, essentially creating an artificial magnetosphere like the one that protects Earth. But magnetic fields consume power and only work on charged particles, not on neutral atoms or dust grains. Some designs propose a sacrificial shield, a large disk of material positioned ahead of the spacecraft to absorb impacts. If a larger object is detected in time, you might attempt to maneuver around it. But at 10% light speed, you are covering roughly 30 million meters every single second. Detection and course correction would need to happen almost instantaneously. Then there is radiation to consider. Space is saturated with cosmic rays. High-energy particles streaming from exploding stars, black holes, and other violent cosmic events. Earth's magnetic field and atmosphere shield us from most of this bombardment. In deep space, there is no such protection. Cosmic rays can shred DNA, elevating cancer risk and causing radiation sickness. The spacecraft hull would provide some degree of shielding, but halting high-energy cosmic rays requires thick, heavy materials. Once again, this adds mass. Some particles are so energetic that they will punch through almost anything you can throw in their path. The crew would accumulate a cumulative radiation dose over 42 years that would be far beyond anything considered safe on Earth. Cancer rates would be significantly elevated. Some crew members would develop tumors, cataracts, and other radiation-linked illnesses. There is no way around this using current technology. It is a calculated risk, one that any volunteer for such a mission would have to accept up front. Communication with Earth introduces yet another layer of psychological difficulty. At the start of the voyage, radio signals would take only a few minutes to reach Earth. But as the spacecraft pushes farther outward, that delay grows relentlessly. 1 light year out, messages take 1 full year to arrive. 2 light years out, 2 years. By the time you reach the midpoint of the journey to Alpha Centauri, messages require more than 2 years each way. A single round-trip conversation takes more than 4 years. You send a message asking a question. 4 years later, you receive an answer. By that point, the context has shifted dramatically. You have probably forgotten what you originally asked. The people you are corresponding with may have retired, moved on, or passed away entirely. Communication transforms into an exchange of letters stretched across time, not anything resembling a conversation. News from Earth would arrive years out of date. Political situations, cultural trends, technological advances, all of it would already be history by the time you learned about it. The spacecraft crew would be culturally frozen in the year of their departure. Earth would continue moving forward without them. By the time they reach Alpha Centauri, Earth might have changed beyond all recognition. The mission that originally launched them might have been forgotten or abandoned. There might not even be anyone on Earth still listening for their transmissions anymore. The isolation is profound in a way nothing else in human experience can match. You would be more alone than any person has ever been in the history of our species, separated not only by physical distance but by time itself. Cut off from every person and everything you ever knew. And then there is the question of what actually happens when you arrive. After 42 years, you reach Proxima Centauri. Now what? You cannot simply touch down on Proxima Centauri b, even assuming it turns out to be habitable in the first place. The spacecraft is traveling at 10% of light speed. To enter orbit around anything, you would need to decelerate, which requires precisely as much energy as the acceleration that got you up to speed in the first place. If your propulsion system accelerated you to 10% light speed over the course of several years at the beginning of the journey, you would need to flip the spacecraft around and decelerate for several more years at the far end. This means you would need twice as much fuel as naive calculation suggests, or you would need an alternative deceleration method. One proposal is the magnetic sail. As you approach the target star, you deploy a large loop of superconducting wire, creating a powerful magnetic field. This field interacts with the star's solar wind, the charged particles streaming outward from the star, producing drag that gradually slows you down. The problem is that solar wind is quite weak. Deceleration would proceed slowly, potentially taking years or even decades. And it only works if the target star produces a vigorous solar wind, which red dwarfs like Proxima Centauri simply do not. Another possibility is using the destination star's own light. Deploy a light sail and let the star's photons bleed off your momentum. Again, this takes time and demands precise orientation. Or you could simply carry extra fuel, but that makes the spacecraft substantially heavier, which requires more fuel to accelerate the initial mass, which makes it heavier still. This is the tyranny of the rocket equation. Every kilogram of payload requires multiple kilograms of fuel to move it. If you cannot slow down, you are stuck doing a flyby. You scream past Proxima Centauri at enormous speed, snapping pictures and gathering measurements for a handful of hours or days, and then you are gone, tumbling off into deep space with no way to stop or turn around. All that effort, 42 years of travel, for a fleeting glimpse. Let's say you do manage to successfully decelerate and settle into orbit around Proxima Centauri b. What would you actually find there? Proxima Centauri is a red dwarf, much smaller and cooler than our Sun. It possesses only about 12% of the Sun's mass, and radiates less than 1% of the Sun's light. For a planet to be warm enough for liquid water, it would have to orbit extremely close, much closer than Earth orbits the Sun. Proxima Centauri b circles its parent star once every 11.2 days, at a distance of only about 4.6 million miles, or 7.5 million kilometers. That is about 5% of the Earth-Sun distance. At that proximity, the planet is almost certainly tidally locked, meaning one hemisphere permanently faces the star, in the same way our moon always presents the same face to Earth. One hemisphere would lie in eternal daylight, the other in eternal darkness. The day side might be scorched into rock, the night side frozen solid. Any habitable zone would exist as a narrow ring around the terminator, the boundary line between day and night where temperatures might be something approaching moderate. But even if conditions somehow allow for liquid water, Proxima Centauri is an extremely active star. It generates powerful flares, sudden outbursts of radiation and charged particles. These flares can be hundreds of times more intense than the flares of our own Sun. A planet orbiting so close would be bathed in that radiation on a regular basis. Unless the planet possesses a strong magnetic field to deflect the radiation, its surface would be regularly sterilized. Any life would have to exist deep underground or beneath extensive oceans. The atmosphere, if one exists at all, might be gradually stripped away over time by the stellar wind and the flares. So Proxima Centauri b might not turn out to be the welcoming, Earth-like world we hope for. It might be a radiation-blasted slab of rock with no atmosphere at all, or a frozen wasteland, or something in between. We will not know until we get there. And that is the gamble. You are committing 42 years, possibly your entire remaining life, to reach a destination that could be completely hostile to human existence. There is no guarantee of success, no way to know in advance whether the voyage will prove worthwhile. You would be betting everything on incomplete data and wildly optimistic assumptions. Let us consider the crew's perspective directly. You volunteer for this mission, fully aware that you will spend 4 decades inside a metal tube, fully aware that you will never return to Earth, fully aware that you will age and might not even live to see the destination. Why would anyone ever agree to this? For some, it would be the adventure itself, the opportunity to be part of something genuinely historic, to be among the first human beings to abandon the solar system and visit another star. For others, it might be escape, leaving behind problems on Earth for a clean start somewhere new, even if that start is 4 light years away. Some might be driven by raw scientific curiosity, the hunger to see what is out there, to resolve the question of whether life exists beyond Earth. And some might choose to go because they believe humanity's future depends on becoming an interstellar species, spreading to other stars as a hedge against extinction. But whatever the motivation, the volunteers would be giving up absolutely everything: family, friends, careers, the chance to raise children who grow up on Earth. They would be stepping into a one-way journey with no possibility of reversal. Training for such a mission would consume years. The crew would need expertise in engineering, medicine, agriculture, physics, chemistry, psychology, and dozens of other specialized fields. They would need to learn how to work alongside one another, to diffuse conflicts, to make decisions by consensus, or to follow a chain of command. They would be run through simulations, enduring months or years of isolation on Earth to determine whether they could actually handle the psychological strain. Some would wash out. Some would be pulled from the program for medical or psychological reasons. Only the most resilient, adaptable, and capable individuals would make the final cut, and even they would struggle mightily. The launch itself would be a deeply emotional affair, saying farewell to loved ones, knowing you will never lay eyes on them again, watching Earth shrink in the rear cameras, becoming a blue dot, then just another unremarkable star, then finally vanishing into the background of space. The first few years might feel exciting. The novelty of the mission, the pride of being selected, the camaraderie of the crew. But after a handful of years, routine sets in. Every day becomes identical to the last. Wake up, eat breakfast, work your shift, exercise, eat dinner, perhaps a bit of recreation, sleep, repeat. The walls close in. The faces around you become painfully familiar. Small annoyances inflate into massive irritations. The smell of recycled air, the constant hum of machinery, the unrelenting knowledge that you cannot leave, cannot go outside, cannot see a tree, cannot feel rain on your skin. It wears on you. Some people would cope by burying themselves in work, keeping themselves constantly busy to avoid thinking about where they are. Others would turn inward, toward meditation, art, writing. Relationships would form, people pairing off for companionship and emotional support. Children might be born aboard the spacecraft, though that raises extraordinarily complicated ethical questions. Is it fair to bring a child into existence aboard a spacecraft, knowing that child will spend their entire childhood, and possibly their entire life, in that environment? Children born during the voyage would grow up having never experienced Earth. To them, the spacecraft would be normal. They would learn about Earth from video recordings and stories, but it would feel distant, almost mythological. By the time they reach adulthood, they might have absolutely no desire to return to a place they have never known. Discipline and governance would be absolutely critical. Who is in charge? How are decisions made? What happens if someone violates the rules, commits a crime, turns violent or uncooperative? On Earth, there are police, courts, prisons. Aboard a spacecraft, options are severely limited. You cannot imprison someone for years without wasting precious crew resources. Exile is not on the table, there is nowhere to send them. In extreme situations, you might have to confine someone to a small cabin, or even consider euthanasia if they become a genuine danger to others. These are horrifying choices to contemplate, but in a closed environment with no outside help, they might become unavoidable. Mission planners would need to establish a legal framework, a system of justice that the crew agrees to before launch. As the years stretch on, technology back on Earth would continue to advance. By the time the Alpha Centauri crew is halfway through their voyage, 20 years in, Earth might have developed faster propulsion systems. A second mission might launch, outfitted with newer technology, traveling at 20 or 30% of light speed. That ship would overtake the first crew, arriving at Alpha Centauri decades earlier than the original mission. The first crew would spend 42 years in transit, only to arrive and discover that Earth has already established a colony there, set up by a later mission that passed them along the way. This is known as the weight calculation, an actual concept in serious interstellar travel discussions. If technology is continuously improving, is it smarter to wait and launch later with superior technology, or to launch now and accept that you might be obsolete by the time you arrive? There is no clean answer. If everyone waits, no one ever actually goes. But if you go too early, you squander resources on a slow mission that gets leapfrogged. Now imagine that you are part of that first crew. You are 30 years into a 42-year journey. You have sacrificed everything. Spent 3 decades locked in confinement. And then you receive a message from Earth. They have constructed a faster ship. It is going to arrive before you do. Your mission, your sacrifice, all of it has been rendered functionally meaningless. How would you feel? Angry? Betrayed? Devastated? Or perhaps relieved? Relieved that at least someone will get there. That the goal you have been laboring toward will actually be achieved. even if not by you. This is the kind of psychological challenge no amount of training can truly prepare you for. Let us assume the first crew does arrive, and they become the first humans to reach Alpha Centauri. They settle into orbit around Proxima Centauri b. They send probes down to the surface, analyze the atmosphere, study the geology, search for any signs of life. Whatever they find would determine the next phase of the mission. If the planet turns out to be habitable, or at least survivable with technological assistance, they might attempt to land and establish a colony. This would require equipment carried with them from the start: habitats, life support systems, tools for mining and manufacturing. They would need to become entirely self-sufficient, producing their own food, water, and air, repairing and constructing new equipment as needed. If the planet turns out to be inhospitable, they would have to live in orbit or on a moon. If Proxima Centauri b even has any moons to speak of, they would be permanently dependent on the spacecraft. In either scenario, they are stuck. There is no returning home. The journey consumed all their fuel. Even if they somehow managed to refuel, the return trip would take another 42 years. By that point, they would all be over 100 years old. No one would survive. They would have to build a new life in the Alpha Centauri system, knowing that Earth is unreachably far away. Communication with Earth would continue, but with the 4-year delay, conversations would be slow and maddening. They would send reports, images, data back to Earth, and Earth would respond with messages of encouragement, updates on new missions, perhaps instructions. But the crew would be fundamentally on their own. And here is a particularly chilling thought. What if something goes wrong during the voyage? What if a critical system fails? The life support, the reactor, food production, water recycling. If the failure happens early enough in the voyage, you might be able to turn back. But if it happens at the halfway point or beyond, you are too far from Earth to return, and too far from Alpha Centauri to reach the destination before the failure kills you. You are stranded in the void. There is no rescue coming. No one can reach you. You would have to fix the problem with whatever resources are currently aboard, or it would be the end. The entire crew dead, drifting through interstellar space aboard a silent spacecraft. Decades later, another mission might stumble upon you. A tomb ship filled with the frozen remains of the crew. A monument to the risks of interstellar travel. This has happened before, in a sense. Early explorers on Earth faced analogous risks. Expeditions to the Arctic, the Antarctic, remote islands. Many simply vanished, never to be heard from again. Their fates were sometimes discovered years or even centuries later. Interstellar travel would be the same, except the timescales are longer, the distances are greater, and the consequences are more absolute. Another scenario to consider. What if the crew discovers something unexpected at Alpha Centauri? Not just a planet, but signs of intelligent life, ruins of an ancient civilization, or active alien technology, or even living extraterrestrials. First contact with an extraterrestrial intelligence would constitute the most significant event in the entirety of human history. But it would also be absolutely terrifying. The crew would be alone, representing all of humanity, making decisions that could affect our entire species. How do you communicate with an alien intelligence? What if they are hostile? The crew would possess no weapons capable of defending against an advanced civilization. What if the aliens have technology far beyond our own? The crew's reports back to Earth would require 4 years to arrive. Earth's advice would require another 4 years to return. By that point, the situation would have evolved beyond recognition. The crew would be forced to make first contact decisions on their own, with no guidance, no backup, and the fate of humanity potentially hanging on their choices. Or what if they find evidence that life once existed but went extinct? A dead world, once teeming with living things, now utterly silent. What killed them? Disease, war, environmental collapse, a cosmic catastrophe. And could the same fate befall Earth? The psychological weight of such a discovery would be profound. On the other hand, what if they find nothing? No life, not even microbial, just a barren rock orbiting a red dwarf. After 42 years of travel, all that sacrifice, and the result is nothing. Empty space, lifeless worlds, No answers to the questions that drove the mission. That would be a different kind of devastation. Not physical, but existential. The recognition that we might truly be alone, that life might be so rare that even traveling to the nearest star yields absolutely nothing. Let's talk about the cost of such a mission. Not merely the financial cost, though that is staggering, but the cost in human terms. The crew would be sacrificing their lives. Their families would be losing them, saying goodbye forever. Earth would be pouring enormous resources, money, materials, expertise into a mission that offers no immediate return and might fail completely. Is it worth it? That is a question each generation has to answer for itself. Some would say no. The resources spent on an interstellar mission could be directed at solving problems on Earth. Poverty, disease, climate change, education. Why spend trillions on sending 100 people to another star when billions on Earth are suffering? Others would argue that exploration is what makes us human in the first place. We have always pushed beyond the horizon, hunting for new lands, new knowledge, new possibilities. Interstellar travel is the next chapter of that journey. And if we refuse to go, if we turn inward and fixate only on Earth, we are limiting our potential, possibly dooming ourselves to extinction if a catastrophe strikes our planet. There is also the long-term perspective to consider. Humanity has existed for roughly 300,000 years, recorded civilization for about 5,000 years. Our industrial age is only about 250 years old. Space travel has existed for less than 70 years. We are infants in cosmic terms. If humanity survives for another 1,000 years, another 10,000, another million, then a 42-year journey to Alpha Centauri will seem like a trivial first step. Our descendants might look back at the first interstellar missions the way we now look back at Columbus or Magellan as the beginning of something much larger, but we have to take that first step. Someone has to go, knowing the risks, accepting the sacrifices, and hoping that whatever they find makes it worthwhile. Would you go? Imagine you are offered a slot on the crew. All expenses paid, the best training in the world, a guaranteed place in history. But you leave Earth forever. You spend the rest of your life in space. You might arrive at a new world, or you might not make it along the way. There are no guarantees. Would you accept? Some people would say yes immediately. The adventure, the legacy, the opportunity to see another star up close, it would be worth any price. Others would refuse without hesitation. The thought of leaving Earth, never seeing a natural sky again, never walking on grass or swimming in an ocean, it would simply be too much to surrender, and both answers are valid. There is no right or wrong choice, it is deeply personal. But the fact that we can even have this conversation, that interstellar travel sits within the realm of theoretical possibility, is itself remarkable. 100 years ago, this would have been pure fantasy. Now it is engineering and physics and economics. We can calculate what it would take. We can design the spacecraft, at least on paper. We can estimate the costs and the timelines. It is not easy. It is not happening tomorrow, or even in the next few decades. But it is possible. And that means that someday, someone will go. The terrifying journey to Alpha Centauri will happen. Perhaps not in our lifetime, but eventually. And when it does, the people who go will be among the bravest humans ever to have lived. They will be leaving behind everything they know, everyone they love, for a destination they might never reach, driven by curiosity and hope, and the belief that what lies out there is worth finding. Now let us consider the broader implications. If we do manage to establish a presence at Alpha Centauri, what does that actually mean for humanity? We would become a two-star species, with populations in both the solar system and the Alpha Centauri system. These populations would be separated by more than 4 light years, with communication delays of at least 8 years for a round-trip message. They would diverge culturally, politically, even biologically over time. Different environments would select for different traits. Lower gravity might favor taller, thinner body types. Higher radiation might favor individuals with better DNA repair mechanisms. Over thousands of years, the populations might become distinct enough that they would be classified as separate subspecies, or even as different species altogether. This is speculative, but it is based on how evolution works. Isolated populations diverge. And 4 light years, is about as isolated as any two populations can possibly be. The Alpha Centauri colony would need to be self-sufficient from day one, but they would also want to maintain ties to Earth. Physical trade is not practical. Shipping physical goods between star systems would take decades. But information can be shared easily. Scientific discoveries, cultural works, technological innovations. All of this can be transmitted via radio or laser communication. Earth benefits from the colony's research and observations. The colony benefits from Earth's larger population and resource base. It is a symbiotic relationship, even if delayed by years. But there is also potential for conflict. What if the colony wants independence? What if they disagree with Earth's political or economic systems? What if Earth attempts to assert control, claiming ownership of the colony, because Earth funded the mission? These are questions humanity would have to grapple with. We would need to establish frameworks for interstellar governance, laws that apply across light years, dispute resolution mechanisms that account for communication delays. It is a new frontier, not just physically, but legally, politically, and socially. There is also the question of follow-up missions. Once the first crew arrives, would Earth send more? A second wave of colonists, additional supplies, updated technology? Or would the colony simply be left to fend for itself, a distant outpost that Earth gradually forgets about? The answer would depend on what the first crew actually finds. If Proxima Centauri b turns out to be habitable and resource-rich, Earth would have strong incentive to send more missions, establishing a larger, more permanent presence. If the planet is marginal or hostile, the colony might remain small, more of a scientific outpost than a true settlement. And then there is the possibility of expansion beyond Alpha Centauri. Once you have proven that interstellar travel is possible, once you have established a colony at another star, the natural next step is to go farther. From Alpha Centauri, you could launch missions to other nearby stars. Barnard star, 6 light-years away. Wolf 359, 7.9 light-years. Lalande, 21,185, 8.3 light-years. Each of these stars has planets, or is at least strongly suspected to. Each could be a potential home for humanity. Over centuries, we could spread through the local neighborhood of the Milky Way, establishing colonies at dozens or even hundreds of stars. Each colony would be independent, separated from the others by enormous distances, but connected by radio signals and shared heritage. Humanity would become a true interstellar civilization, no longer confined to a single star, no longer vulnerable to a single catastrophic event wiping us out. But this is all long-term speculation. The first step is Alpha Centauri, and that first step is terrifying. It is a journey that tests the limits of technology, psychology, and human endurance. It requires sacrifices most people cannot even begin to imagine. It offers no guarantees, no certainty of success. But it is also deeply inspiring. The idea that we could reach beyond our own solar system, that we could visit another star, that we could find new worlds and possibly even new life, it captures the imagination in a way that few other endeavors can. It is the ultimate exploration, the final frontier, the culmination of millions of years of evolution that produced a species capable of leaving its home star. And when it happens, when the first humans set foot in another star system, it will be one of the greatest moments in history. Not just human history, but the history of life itself on Earth. For billions of years, life has been confined to this one planet. With interstellar travel, we shatter that confinement. We become something new, a species that spans the stars. Tonight, we have explored what it would truly take to reach Alpha Centauri. We have looked at the distances, the technologies, the challenges, the psychological toll, the risks, and the potential rewards. We have confronted the terrifying reality that such a journey is, by any honest measure, one of the most difficult things humanity could attempt. It is not simply a matter of constructing a spacecraft and aiming it at another star. It is decades of travel in a confined environment with no escape, no resupply, and no guarantee of survival. It is isolation on a scale we have never experienced before. Separation from Earth by distances that make real-time communication utterly impossible. It is the knowledge that you are leaving everything behind. Every person you know, every place you have ever been, for a destination you have only seen as a point of light in the sky. And yet, despite all of this, despite the fear and the difficulty and the unknown, there will be people who volunteer. There will be engineers who dedicate their lives to designing the spacecraft. There will be scientists who spend entire careers figuring out the propulsion, the life support, the navigation. There will be crew members who step aboard that spacecraft, strap themselves in, and launch into the void, knowing that they might never return. Because that is what humans do. We explore, we push boundaries, we ask what is over the next hill, across the next ocean, around the next star, and we go find out. The journey to Alpha Centauri is terrifying, but it is also inevitable. Someday we will go. And when we do, those travelers will carry with them the hopes and dreams of everyone who ever gazed up at the night sky and wondered what was out there. They will be our ambassadors to the cosmos, representing the very best of what humanity can be. Courage, curiosity, determination, and hope. The nearest star is 4.24 light-years away, 25 trillion miles of empty space, filled with radiation and dust, and the cold vacuum of the void. Getting there will demand everything we have. It will require technology we have not yet developed, courage we have not yet tested, and sacrifices we have not yet made. But we will do it. Not tomorrow, not next year, but someday. And when that day finally arrives, when the first spacecraft leaves the solar system bound for Alpha Centauri, it will mark the beginning of humanity's greatest adventure, the journey to the stars. Thank you for joining me tonight on this exploration of what it would take to reach our nearest stellar neighbor. If you found this journey as fascinating and unsettling as I did, please take a moment to like this video and subscribe to the channel. It helps more than you know. And remember, the next time you look up at the night sky and see Alpha Centauri, a faint point of light in the southern sky, you will now know what it would really take to get there. The distance, the danger, the sacrifice. And maybe, just maybe, you will understand why we will go anyway. Sleep well tonight, knowing that somewhere out there, 4 light-years away, sits another star, possibly with planets, possibly with life. And someday, we are going to find out. But before we end tonight's journey, there is more we need to understand about what makes this trip so uniquely challenging. Let us dig deeper into some of the specific obstacles that would turn a journey to Alpha Centauri into one of the most harrowing experiences imaginable. Let's start with navigation. You might assume that pointing a spacecraft at Alpha Centauri and firing the engines would be relatively straightforward. It is anything but. Space is three-dimensional, constantly shifting, and navigation at interstellar distances requires precision we have never before attempted. Alpha Centauri appears stationary in our night sky, but that is an illusion. Every star in the galaxy is in motion, orbiting the galactic center at different speeds and in different directions. Our own sun is moving through space at approximately 500,000 miles per hour, or roughly 800,000 kilometers per hour, relative to the cosmic microwave background. Alpha Centauri is moving at a different velocity in a different direction. This means the target is not actually where it appears to be. By the time light from Alpha Centauri reaches us, showing us where the star was 4 years ago, the star has moved. You have to calculate where it will be when you arrive 42 years in the future and aim for that position. This is called leading the target, like shooting at a moving object, except the target is moving through three-dimensional space at hundreds of thousands of miles per hour. And you are also moving, and both of you are being influenced by the gravity of other stars, the galactic center, and dark matter we cannot even see. The calculations are phenomenally complex. A tiny error in your initial trajectory, even a fraction of a degree, compounds over years and light years until you miss your target by millions of miles. You would need constant course corrections throughout the journey, tiny burns of the engines to adjust your path. But here is the problem. Those engines need fuel. Every course correction consumes fuel. Fuel you cannot replace. If you run out halfway through the voyage, you are stuck on whatever path you are on. You might miss Alpha Centauri entirely, flying past it into deep space with no way to turn around. And navigation demands instruments. Telescopes to track your position relative to known stars, accelerometers to measure your velocity, gyroscopes to maintain your orientation. All of this equipment needs to work flawlessly for decades. If a telescope's mirror gets cracked by a micrometeorite strike, your ability to navigate accurately degrades. If a gyroscope fails, you might not even know which direction you are facing. Redundancy is essential, but every backup system adds weight. There is also the problem of relativity. We have already discussed time dilation, but there is another effect called relativistic beaming. As you approach significant fractions of the speed of light, the light from stars ahead of you shifts toward blue wavelengths, while stars behind you shift toward red. This is Doppler shift, the same effect that makes a police siren sound higher pitched as it approaches and lower as it moves away. At 10% of light speed, the Doppler shift becomes noticeable. Alpha Centauri, which appears yellow from Earth, would start to look bluer as you approach. Stars behind you would redden. This affects navigation because the stars you are using as reference points do not look the way they do from Earth. Your star charts become less reliable. You need to account for relativistic effects in your calculations, adding another layer of complexity. Now let us talk about the spacecraft structure itself. At 10% of light speed, the stresses on the ship are immense. Any acceleration or deceleration creates g-forces that the structure has to withstand. If you accelerate too quickly, the ship could tear itself apart. Imagine a spacecraft several hundred meters long. The engines are at one end, pushing. The rest of the ship is being pulled along by that thrust. The connection points between sections experience enormous forces. If a joint is weak, if a weld has a microscopic flaw, it could fail and sections of the ship could separate. Materials science becomes absolutely critical. You need materials that are strong yet light. Titanium alloys, carbon fiber composites, advanced ceramics. Every component needs to be tested beyond normal limits because there is no room for failure. One structural failure could doom the entire mission. And then there is thermal expansion and contraction. In space, temperatures vary wildly. The side of the ship facing the direction of travel might be bombarded by high-energy particles and dust, generating heat. The side facing away radiates heat into the coldness of space. This creates temperature gradients across the structure. Materials expand when heated and contract when cooled. If different parts of the ship are at different temperatures, they expand and contract at different rates. Over time, this can cause stress fractures, warping, misalignment of critical components. Engineers would need to design the ship with thermal management in mind, heat pipes to distribute warmth evenly, insulation to protect sensitive areas, radiators to shed excess heat. All of this adds complexity and weight. The rotating sections that provide artificial gravity create their own challenges. Rotation generates centrifugal force, but it also creates stress on the structure. The outer hull experiences constant outward pressure. Imagine a spinning cylinder. The faster it spins, the more force pushes outward, trying to tear it apart. This is why the rotation rate has to be carefully controlled. Too fast, and the structure fails. Too slow, and the artificial gravity is too weak. And if the rotation is uneven, if one section spins faster than another, you get wobbling. This wobble can amplify over time, becoming more and more severe until the whole ship is tumbling out of control. Stabilization systems, gyroscopes, and reaction wheels would be needed to maintain smooth rotation. But these systems require power and maintenance. Let's discuss the human factor more deeply. We have touched on the psychological challenges, but the reality is even more complex than we have admitted. Humans are social creatures, evolved to live in communities with variety and change. The spacecraft environment is the exact opposite. The same people, the same spaces, the same routines for decades on end. Studies of isolated groups like those in Antarctic research stations or submarines show predictable patterns. In the first few weeks or months, everyone is excited, cooperative, motivated. This is called the honeymoon phase. Then reality sets in. The novelty wears off. Irritations begin. Small habits that seemed quirky at first become infuriating. The way someone chews their food, a laugh that is too loud, someone who talks too much or not enough. These annoyances build up, creating tension. This is the conflict phase, and it can last for months or years. Arguments erupt over trivial things. Cliques form. People stop communicating except when absolutely necessary. The social fabric of the crew starts to fray. In isolation studies on Earth, this is when people drop out, request transfers, or suffer mental breakdowns. But on an interstellar spacecraft, there is no dropping out, no transfer, no escape. You have to find a way through it. Eventually, if the crew survives the conflict phase, they might reach acceptance. This is when people make peace with their situation. They accept the limitations, adjust their expectations, and find ways to coexist. But not everyone reaches this phase. Some people never adjust. They remain angry, depressed, or withdrawn for the duration. Mission planners would need to screen for psychological resilience, but there is no perfect test. You cannot simulate 42 years of confinement. The best you can do is approximate it with shorter isolation periods and hope that predicts who will cope and who will not. Relationships and intimacy add another layer. People will form romantic relationships. This is natural and probably healthy, providing emotional support and comfort. But relationships also bring complications: jealousy, breakups, love triangles. What happens when a relationship ends badly, and the two people still have to work together every day for decades? What if they both want to avoid each other, but the ship is so small there is no way to do that? And what about reproduction? If people are having sexual relationships, pregnancies are likely. Birth control can fail. Even with the most reliable methods, over 42 years and a crew of 100, you would probably have some unplanned pregnancies. Pregnancy and childbirth in space present medical challenges. We do not fully understand how microgravity or even artificial gravity affects fetal development. Studies on animals suggest there could be issues with bone formation, muscle development, and organ placement. Human pregnancies have never been attempted in space, so we do not know what to expect. And even if the pregnancy goes smoothly, raising a child on a spacecraft is a profound ethical question. That child did not choose to be on this voyage. They will grow up in a confined space, never experiencing Earth. Is that fair to them? Some would argue that it is not, that bringing children into such an environment is cruel. Others would say that life is precious wherever it occurs, and children could bring joy and hope to the crew. There is no easy answer. Mission planners would need to establish policies. Are pregnancies allowed, encouraged, forbidden? If a pregnancy occurs, is abortion an option? These are deeply personal questions with no universally right answer, but they would need to be addressed before launch. Education would be critical. If children are born on the ship, they need to be educated. Not just basic reading and math, but engineering, medicine, science. They would need to be trained to maintain the ship and contribute to the mission. The crew would essentially be running a school alongside everything else. Cultural preservation becomes important too. The crew would bring music, books, films, art from Earth. These cultural artifacts help maintain a connection to home, remind people of where they came from. But over time, the crew would create their own culture. New art, new music, new stories based on their unique experience. They would develop their own traditions, holidays, rituals. By the time they arrive at Alpha Centauri, they might have a culture that is distinct from Earth, a blend of what they brought and what they created along the way. Language might even evolve. Over 42 years, especially if children are being raised on the ship, language could drift. New words would be invented for spacecraft-specific concepts. Old words might fall out of use. Slang would develop. By the end of the voyage, the crew might speak a dialect that is difficult for people on Earth to fully understand. Now let us consider the possibility of something going catastrophically wrong. Not just a system failure, but a complete disaster. A reactor breach flooding the ship with radiation. A collision with a larger object that punches through the hull, causing rapid decompression. A fire in the life support section, destroying the equipment that produces oxygen. Any of these scenarios would be fatal. The crew would have minutes to hours before it is over for everyone. There would be no rescue, no way to call for help that would arrive in time. They would have to solve the problem themselves or perish. Let us walk through a scenario. Imagine a micrometeorite impact, a grain of sand-sized object traveling at 10% light speed from the opposite direction. Relative velocity is 20% light speed. The kinetic energy is enormous. It punches through the forward shield, through the outer hull, and into the habitat section. The impact creates a hole the size of a dinner plate. Air rushes out. Pressure drops. Alarms scream. The crew has seconds to react. Emergency protocols kick in. Airtight doors slam shut, sealing off the breached section. This saves most of the ship, but anyone in the breached section is cut off. If they are not wearing suits, they have about 15 seconds of useful consciousness before hypoxia sets in. The rest of the crew scrambles. They need to assess the damage, figure out which section is breached, determine if it can be repaired. If the breach is in a critical area, like the life support system, the entire mission is at risk. They would need to jury-rig a repair, patch the hole from the inside or outside. This requires someone to go EVA, extravehicular activity, putting on a spacesuit and going outside the ship. But remember, the ship is traveling at 10% light speed. The cosmic ray flux outside is intense. Any EVA exposes the person to lethal radiation doses. They might complete the repair and save the ship, but they would be sacrificing their own future. Cancer within months, radiation sickness, a slow, painful decline. Someone would have to volunteer, knowing they are sacrificing themselves to save everyone else. That is the kind of impossible choice that could arise. Or consider a different scenario. A pathogen outbreak. Despite all the screening and quarantine procedures before launch, a virus or bacteria makes it aboard. Maybe it was dormant in someone's body, activated by stress or radiation. Maybe it mutated in the unique environment of the spacecraft. It starts spreading. People get sick. Fever, coughing, weakness. The medical team tries to contain it, isolate the infected, treat symptoms, develop a cure or vaccine. But medical resources are limited. If the pathogen is aggressive, if it spreads faster than they can control, it could wipe out the entire crew. And even if they contain it, they might have to make terrible decisions. Quarantine the infected in a sealed section with no treatment, letting nature take its course to prevent the disease from spreading. Euthanize someone who is infected and suffering with no hope of recovery. These are nightmare scenarios, but they are realistic possibilities. Interstellar travel does not just test your technology. It tests your humanity. It forces you to confront situations where there are no good options, only varying degrees of bad. And you have to live with the consequences of your choices for the rest of the voyage. Let us shift to thinking about what arrival at Alpha Centauri would actually be like. You have spent 42 years traveling. You are exhausted, aged, scarred by the journey. But you made it. Alpha Centauri grows larger in the viewports. No longer a point of light, but a visible disk. You are still months away from closest approach, but the anticipation builds. You begin detailed observations. Telescopes focus on Proxima Centauri b, the planet you have come to explore. You measure its size, mass, orbital characteristics. You analyze the spectrum of light reflecting off it, looking for signs of an atmosphere, water vapor, oxygen, methane. These signatures would tell you if the planet is habitable or if it is a dead rock. The data comes in. Proxima Centauri b is indeed rocky, slightly larger than Earth. There is an atmosphere, mostly carbon dioxide and nitrogen. No free oxygen, which means no photosynthetic life-producing oxygen, at least not in large quantities. Surface temperature measurements show extreme variation. The day side is blistering hot, over 300 degrees Celsius, or 572 degrees Fahrenheit. The night side is frozen, below -100 degrees Celsius, or -148 degrees Fahrenheit. The habitable zone, if it exists, would be a narrow band around the terminator. Further analysis shows the planet is indeed tidally locked, one face always toward the star. The atmospheric circulation is bizarre. Hot air rises on the day side, flows high in the atmosphere to the night side, cools and sinks, then flows back along the surface. This creates permanent hurricane-force winds at the terminator, the boundary between day and night. Landing there would be incredibly challenging. And then there is the radiation. Proxima Centauri is an active star. You detect flares, sudden bursts of X-rays, and charged particles. These flares happen every few days, bombarding the planet with radiation. Without a strong magnetic field, the surface is being sterilized regularly. Any life would need to be deep underground or in subsurface oceans. The crew debates, is it worth landing on such a hostile world? Would it be better to stay in orbit, send down robotic probes, and conduct research from the safety of the ship? But after 42 years, the temptation to set foot on another world is overwhelming. A landing team is assembled. They will descend in a shuttle, land in the Terminator zone, set up a temporary habitat, and explore. The descent is tense. The shuttle fights against the winds, buffeted by gusts that threaten to flip it over. The pilot, trained for decades for this moment, manages to land safely. The team disembarks, stepping onto the surface of Proxima Centauri b, the first humans to set foot on a world beyond the solar system. They are wearing heavy suits designed to protect against the radiation and the temperature extremes. The sky is alien. The star Proxima Centauri hangs on the horizon, a deep red, much dimmer than the sun. It casts an eerie red light over the landscape. The terrain is rocky, barren, with no vegetation, no obvious signs of life. But there is something strange: patterns in the rock, layers that suggest sedimentary deposition. This rock was formed underwater. There was liquid water here, maybe millions of years ago, before the star's flares stripped away the atmosphere and boiled the oceans. The team takes samples, drills into the ground, searches for fossils, any evidence of past life. And then they find it. A layer of rock rich in organic compounds, chemical signatures consistent with biological processes. Not life now, but life that existed long ago. Proxima Centauri b was once a living world. And then something happened. The star's activity increased, the radiation intensified, and life was extinguished. This discovery is monumental, proof that life can arise on other worlds, but also a sobering reminder of how fragile it is. If Earth's sun were as active as Proxima Centauri, life on Earth might never have developed, or it might have been wiped out before it could evolve intelligence. We got lucky. Our sun is calm, stable, and Earth has a magnetic field that protects us. Proxima Centauri b had neither of those advantages. The crew sends the data back to Earth, a signal that will take 4 years to arrive. Meanwhile, they establish a permanent presence. They build habitats, set up mining equipment to extract resources from the planet, begin manufacturing fuel and supplies. The goal is to make the Alpha Centauri outpost self-sufficient, and they start thinking about the next step: other stars, other worlds. From Alpha Centauri, the nearest stars are different than from Earth. Barnard's star is closer from here than it is from the solar system. The crew could, in theory, continue the journey, but they are old, tired. Most of the original crew who launched from Earth are in their 70s or 80s. Some have passed along the way. The next generation, those who were children when the mission launched or were born on the ship, they are the ones who might continue. They have never known Earth. To them, Alpha Centauri is home. The idea of spending another few decades traveling to yet another star might not appeal. Or maybe it does. Maybe the urge to explore, to see what is beyond the next horizon, is part of who they are. This is how humanity spreads, one star at a time. Each colony becomes a stepping stone to the next. Over centuries, we could establish a network of outposts throughout the local region of the galaxy, each separated by light years, each independent but connected by radio signals and shared knowledge. It is a slow process, measured in human lifetimes and generations, but it is the only way. Unless we develop faster than light travel, which current physics says is impossible, this is the reality of interstellar expansion: slow, dangerous, and utterly transformative. Now let us bring it back to Earth and think about what this mission means for those who stayed behind. You are on Earth, watching the launch of the Alpha Centauri mission. It is a global event. Billions of people watch as the spacecraft lifts off, beginning its journey to another star. There is excitement, pride, hope. Humanity is taking its first step toward the stars. But there is also sadness. The crew members have families, friends, loved ones who are saying goodbye forever. They will never see each other again. Messages can be sent, but with years of delay, it is not the same as a real conversation. Years pass. The spacecraft sends back updates. Everything is going well. The crew is healthy. Systems are functioning. Earth celebrates each milestone. 1 year out, 5 years, 10 years. But as time goes on, interest wanes. The mission becomes background news. People move on with their lives. The crew becomes a distant memory, a footnote in history. And then, 42 years after launch, a message arrives from Alpha Centauri. They made it. They are in orbit around Proxima Centauri b. They are preparing to land. Earth erupts in celebration. The mission succeeded. Humanity has reached another star. But the people who sent the mission are mostly gone. The engineers who designed the spacecraft are retired or deceased. The politicians who funded it are out of office. The children who watched the launch are now in their 40s or 50s with children of their own. The world has changed. New technologies have been developed. Faster propulsion systems are on the drawing board. In another decade or two, Earth might send a second mission that could reach Alpha Centauri in half the time. The first crew's journey, their sacrifice, already feels outdated. And yet, they were first. They proved it could be done. They opened the door for everyone who comes after. That is their legacy. The messages continue. The crew sends back data, images, discoveries. The finding of ancient life on Proxima Centauri b is a revelation. It changes how we see the universe, how we think about our place in it. We are not alone in having life. Even if that life is extinct, the universe is, or was, full of living worlds. And if life arose on Proxima Centauri b, it probably arose on countless other worlds too. Some of those worlds might still have life. Some might have intelligent life. The crew at Alpha Centauri starts thinking about that. They point their telescopes at other stars, looking for signs, radio signals, laser pulses, anything that might indicate technology. They find nothing. The galaxy, as far as they can tell, is silent. Either we are alone, or everyone else is too far away, or they are not broadcasting, or they have gone extinct, like the life on Proxima Centauri b. The silence is both disappointing and humbling. Back on Earth, society continues to evolve. The existence of the Alpha Centauri colony raises questions. Do they have the same rights as Earth? Can they declare independence? What if there is a conflict between Earth and the colony? With a 4-year communication delay, there is no way to have a meaningful negotiation. By the time Earth sends a message and receives a reply, 8 years have passed. Situations can change drastically in that time. Philosophers, lawyers, and politicians debate these issues. New frameworks for interstellar governance are proposed. Some suggest each colony should be fully autonomous, making its own decisions. Others argue Earth should retain ultimate authority since Earth funded and launched the missions. There is no consensus, but the conversation is happening. Humanity is grappling with what it means to be a multi-star civilization. Meanwhile, technology marches on. The breakthrough everyone hoped for does not come. We do not discover warp drives or wormholes. Physics still limits us to slower-than-light travel, but propulsion improves. New engine designs push speeds to 15%, 20% of light speed. The second wave of missions to Alpha Centauri and other stars are faster, safer, more efficient. They build on the lessons learned from the first mission. And eventually, decades after the first landing, Earth sends a colony ship. Not a small crew of explorers, but hundreds or thousands of people intent on establishing a permanent, large-scale settlement. This ship carries the equipment to terraform, to build cities, to create a true second home for humanity. The original crew, those who are still alive, welcome the newcomers. They are elders now, respected for their pioneering journey. They watch as the colony grows, as children run through newly built streets, as farms are established and industry develops. Alpha Centauri transforms from a distant star into a thriving human world. And the process repeats. From Alpha Centauri, missions are launched to other stars. The wave of human expansion ripples outward, slowly but inexorably. This is the long-term vision, not just reaching Alpha Centauri, but using it as a base for further exploration. Each new colony becomes a launching point for the next. Over centuries and millennia, humanity spreads through the galaxy, star by star, world by world. It is a vision that requires patience, sacrifice, and an acceptance of timescales far longer than individual human lives. But it is the vision that drives those who look at the stars and see not just lights in the sky, but destinations, homes, futures. let us consider one final aspect of this journey: the philosophy of it. Why go at all? If the journey is so dangerous, so difficult, so terrifying, why attempt it? What drives the human urge to explore? Part of it is curiosity. We want to know what is out there. Is there life? What are other worlds like? Can we survive beyond Earth? These questions have no answers unless we go and look. Part of it is survival. Earth will not last forever. In about 5 billion years, the sun will expand into a red giant, engulfing the inner planets. Earth will be destroyed. Long before that, perhaps in 1 billion years, the sun will get hot enough that Earth's oceans will boil away. Life as we know it will end. If humanity is still around, we will need somewhere else to go. Spreading to other stars ensures that even if Earth is destroyed, humanity survives. Part of it is the challenge. Humans are at our best when we are solving difficult problems, pushing boundaries, achieving things that seem impossible. Interstellar travel is the ultimate challenge. It requires us to innovate, to cooperate, to think beyond ourselves, and part of it is legacy. We want to leave something behind, to know that we mattered, that we contributed to something greater than ourselves. The crew of an interstellar mission is leaving a legacy that will endure for centuries. They are making it possible for future generations to live among the stars. That is a powerful motivator. But there is also a darker side. The journey to Alpha Centauri would be terrifying, not just because of the physical dangers, but because of the existential ones. You would be confronting the reality of your own insignificance. You are a tiny speck on a tiny ship in an unimaginably vast universe. You are leaving behind everything that gave your life meaning, your family, your culture, your world, for an uncertain future. You would have to come to terms with the fact that you might fail, that you might not make it along the way, that your sacrifice might be for nothing. That is a level of existential dread most people never have to face. And yet some people would embrace it. They would see it as an opportunity to confront the fundamental questions of existence. What does it mean to be human? What is our purpose? Are we significant or insignificant? The journey would force you to grapple with these questions in a way that is impossible in the comfortable confines of Earth. And maybe that is part of the appeal, not despite the terror, but because of it. The journey strips away all the distractions, all the comforts, all the illusions we use to avoid confronting the big questions. It leaves you alone with the universe, with yourself, with the raw reality of existence, and in that confrontation you might find something: meaning, purpose, a deeper understanding of who you are and what you are capable of. Or you might find nothing, just the cold, indifferent void. Either way, you would know. You would have looked into the abyss and survived, or not. That is what makes the journey to Alpha Centauri terrifying. It is not just the risk of not making it. It is the risk of confronting the ultimate questions and discovering answers you are not prepared for. It is the risk of finding out that we are alone, that the universe is empty, that there is no grand purpose, no meaning beyond what we create for ourselves. Or the risk of finding life, intelligence, and discovering that we are not special, that our existence is just one among countless others, no more significant than any other. Both possibilities are frightening in their own way. And yet, we will go, because the alternative, staying on Earth and never knowing, is even more frightening. We are a species that needs to know, that cannot help but explore, that pushes forward into the unknown, despite the risks. That is what makes us human. That is what will carry us to Alpha Centauri and beyond. But before we say goodnight, there is one more dimension to this journey that deserves our attention. The technological hurdles we would need to overcome before such a mission could even launch. We have talked about propulsion systems, but let us be more specific about what each option really involves and why none of them are ready for a mission like this. Chemical rockets, the kind we use today to launch satellites and reach the Moon and Mars, are completely inadequate for interstellar travel. They work by combining fuel and oxidizer in a combustion chamber. The chemical reaction produces hot gases that expand rapidly and are expelled out the back of the rocket, creating thrust. This is efficient enough to get off Earth and even reach other planets in our solar system, but the energy density is too low for interstellar speeds. The fastest speed achieved by a chemical rocket, the Apollo 10 capsule during its return from the Moon, was about 25,000 miles per hour, or about 40,000 kilometers per hour. That is fast enough to circle Earth in less than an hour. But to reach Alpha Centauri at that speed would take over 100,000 years. We need something with far higher energy density. Nuclear propulsion offers better performance. There are several types. Nuclear thermal rockets heat a propellant, usually hydrogen, using a nuclear reactor. The hot hydrogen is expelled through a nozzle, creating thrust. This gives you about twice the efficiency of chemical rockets. Better, but still nowhere near enough for interstellar travel. Then there is nuclear pulse propulsion, which we mentioned earlier. Project Orion, studied in the 1950s and 1960s, proposed using nuclear bombs. You drop a bomb behind your spacecraft, detonate it, and absorb the blast with a massive shock absorber plate. Each explosion would give you a push. Do this thousands of times and you could reach several % of light speed. The engineering is terrifying. The shock absorber plate would need to be incredibly strong to withstand repeated nuclear explosions. It would need to be enormous, maybe 100 meters in diameter or more. The spacecraft behind the plate would need to be protected from radiation and heat. The nuclear weapons themselves would need to be reliable. If one fails to detonate, you have wasted mass and fuel. If one detonates prematurely or too close, it could destroy the shock plate and the ship. And politically, launching thousands of nuclear weapons into space, even for a scientific mission, would be nearly impossible. The Partial Test Ban Treaty of 1963 banned nuclear weapons tests in space. Getting international agreement to exempt an Orion-style spacecraft would require decades of negotiation and might never happen. Project Orion was shelved not because the physics was wrong, but because the politics and practicality made it impossible. Fusion propulsion is more promising in theory. Fusion is what powers the sun. Two hydrogen atoms, usually deuterium and tritium, combine to form helium, releasing energy. The energy released per unit mass is far greater than chemical reactions or fission. If you could sustain a controlled fusion reaction in a rocket engine, you could achieve much higher exhaust velocities, meaning better efficiency and higher speeds. But controlled fusion is hard. Really hard. The challenge is that fusion requires temperatures of millions of degrees and pressures that are difficult to achieve and maintain. On the Sun, the immense gravity provides the pressure. On Earth, we need to create that pressure artificially. There are two main approaches. Magnetic confinement, where you use powerful magnetic fields to contain a plasma at fusion temperatures. This is the basis of designs like tokamaks and stellarators. Or inertial confinement, where you compress a fuel pellet using lasers or other means until fusion occurs. After 70 years of research and billions of dollars in funding, we have achieved fusion reactions in laboratories, but we have not achieved net positive energy output. The energy needed to create the conditions for fusion exceeds the energy released by the fusion reaction. We are close. Experiments like ITER, the International Thermonuclear Experimental Reactor being built in France, might achieve net positive fusion in the coming decades. But going from a laboratory reactor that produces net energy to a compact, reliable fusion rocket engine that can operate continuously for years or decades is another enormous step. It is not impossible, but it is not something we will have in the next few decades. Maybe by the end of this century, if research progresses well and funding continues. Antimatter propulsion is even further out of reach. Antimatter annihilation is the most energy-dense reaction possible. When a particle meets its antiparticle, both are completely converted to energy. The efficiency is 100%. Compare that to fusion, which converts less than 1% of the mass to energy, or chemical reactions, which convert a tiny fraction of a percent. If you had antimatter fuel, you could achieve incredible speeds with relatively small amounts. A few kilograms of antimatter could accelerate a spacecraft to a significant fraction of light speed. The problem is production. Antimatter does not exist naturally on Earth. It is produced in particle accelerators by smashing high-energy particles together. Occasionally, an antiparticle is created. You can capture it using magnetic fields and store it in a magnetic trap. But the production rate is infinitesimally slow. It takes billions of particle collisions to produce a single antiproton. The total amount of antimatter ever produced on Earth is less than 20 nanograms. That is 20 billionths of a gram. Barely enough to power a light bulb for a few seconds. To fuel an interstellar spacecraft, you would need kilograms or tons of antimatter. At current production rates, it would take billions of years to accumulate that much, and the cost would be astronomical. Producing a single gram of antimatter with current technology would cost trillions of dollars. We would need revolutionary advances in production methods. Perhaps a dedicated antimatter factory in space, using solar power or a fusion reactor to run massive particle accelerators. Even then, you would need to store the antimatter. It cannot touch any normal matter, or it annihilates instantly. You would need perfect magnetic containment with redundant systems and backup power. Any failure, even for a fraction of a second, and your entire fuel supply explodes. The energy release would be catastrophic. A single kilogram of antimatter annihilating releases energy equivalent to 43 megatons of TNT. That is roughly the yield of the largest nuclear bomb ever tested, the Tsar Bomba. If your containment fails, your spacecraft becomes a fireball visible across light years. So antimatter propulsion, while theoretically possible, is practically out of reach for the foreseeable future. Ion drives are real and operational, but they are slow. They work by ionizing a propellant, usually xenon gas, and accelerating the ions using electric fields. The exhaust velocity is very high, much higher than chemical rockets, which makes them efficient. But the thrust is tiny. An ion drive produces about as much force as a piece of paper resting on your hand. It takes weeks or months to build up any significant speed. For missions within the solar system, this is fine. You have time. You can run the engine for years, gradually accelerating, and eventually reach high speeds. NASA's Dawn mission used ion drives to visit the asteroids Vesta and Ceres. It worked beautifully. But for interstellar travel, you need more thrust. Even running an ion drive continuously for decades, you would only reach a small fraction of a percent of light speed. Not fast enough. You could scale up the ion drive, make it more powerful, but that requires more electricity. A more powerful ion drive needs megawatts or gigawatts of power. That means larger nuclear reactors, which means more mass, which means you need even more thrust to accelerate that mass. It becomes a vicious cycle. Solar sails avoid the need for carrying fuel. Instead, they use light pressure. Photons from the sun carry momentum. When they reflect off a mirror, they transfer that momentum, producing a tiny push. Build a sail large enough and light enough, and you can accelerate using sunlight alone. No fuel, no engines, just a giant reflective sheet. The problem is that sunlight is weak. At Earth's distance from the sun, light pressure is about 9/millionths of a Newton per square meter. To get useful acceleration, you need a sail that is square kilometers in area, but weighs only a few grams per square meter. That is thinner than tissue paper, but also strong enough to withstand the stresses of acceleration and not tear. Materials science has not achieved this yet. We can make thin, reflective films, but they are either too heavy or too fragile. And even if you solve the materials problem, the sun's light weakens rapidly as you move away from it. By the time you are a few AU out, past the orbit of Mars, the light pressure is so weak that acceleration becomes negligible. You would need a different light source. This is where laser propulsion comes in. Instead of relying on sunlight, you build a massive laser array on Earth, or in orbit. You point it at the spacecraft's sail and blast it with concentrated light. The laser can be much more powerful than sunlight, accelerating the sail to high speeds. The Breakthrough Starshot project envisions exactly this, a ground-based laser array with a total power of 100 gigawatts. That is the output of 100 large power plants. This array would beam light at a tiny spacecraft, maybe a gram in mass, with a sail a few meters across. The laser would push the sail for a few minutes, accelerating it to 20% light speed. Then the laser shuts off, and the spacecraft coasts the rest of the way to Alpha Centauri. It sounds great, but there are challenges. First, the laser array would cost tens of billions of dollars to build. Second, you need to keep the laser focused on a tiny sail that is accelerating away from Earth at thousands of kilometers per second. The precision required is staggering. Any misalignment, and the laser beam misses the sail entirely. You would need adaptive optic systems that adjust the beam in real time to compensate for atmospheric turbulence, if the laser is ground-based, or orbital perturbations, if it is space-based. Third, The spacecraft is so small that it cannot carry much. A few cameras, maybe a basic spectrometer, a transmitter. That is it. You are not sending humans. You are sending a probe that will do a flyby, snap a few pictures, and transmit them back to Earth. And transmission is another problem. With such a small spacecraft, the transmitter's power is limited, maybe a few watts at most. The signal would be incredibly weak by the time it reaches Earth, 4 light-years away. You would need enormous receiving dishes on Earth to detect it, and the data rate would be slow. It might take months or years to transmit a single high-resolution image. Still, Breakthrough Starshot is the most realistic near-term proposal for reaching Alpha Centauri. Even if it is only with a tiny probe, if it works, we could have images of Proxima Centauri b within a few decades. That would be historic, but it is not the same as sending humans. For a crewed mission, we need better technology, systems that do not exist yet. We need propulsion that can accelerate a large spacecraft, hundreds or thousands of tons, to a significant fraction of light speed. We need life support that can sustain people for decades with minimal resupply. We need radiation shielding that actually works against cosmic rays. We need medical technology that can handle any illness or injury that might occur. We need psychological support systems that can keep people sane in isolation for 40 years. None of this is ready. All of it is theoretically possible. But turning theory into practice takes time, money, and effort. Decades at minimum, possibly centuries. And that is assuming steady progress, no major setbacks, and continued funding. Let us talk about funding. Interstellar missions are expensive. Estimates for a crewed mission to Alpha Centauri range from hundreds of billions to trillions of dollars. That is comparable to, or greater than, the entire GDP of some countries. Who pays for this? Governments could fund it. But convincing taxpayers to spend trillions on a mission that will not return results for decades is politically difficult, especially when there are pressing needs on Earth. Poverty, disease, climate change, infrastructure. Private companies might contribute, but the return on investment is unclear. There is no profit in sending people to Alpha Centauri. No resources to extract and bring back. No products to sell. It is pure exploration and science. Some billionaires are interested in space exploration for its own sake. Elon Musk, with SpaceX and Mars. Jeff Bezos with Blue Origin. They might fund or partially fund an interstellar mission as a legacy project. But even their resources, vast as they are, might not be enough for a project this large. International cooperation is probably necessary. A coalition of countries pooling resources, like the International Space Station, but on a much larger scale. The ISS cost about $150 billion over several decades, shared among the US, Russia, Europe, Japan, and Canada. An interstellar mission would cost many times more. But it is possible. If humanity decides this is a priority, if we can set aside national rivalries and work together, we could do it. The question is whether we have the will. And there is another factor: time. The people who decide to fund and launch the mission will not live to see the results. Politicians think in terms of election cycles, a few years at most. Corporations think in terms of quarterly earnings. An interstellar mission requires thinking in terms of lifetimes and generations. That is a hard sell. But maybe, as climate change and resource depletion make Earth's future more uncertain, people will become more interested in ensuring humanity's survival by spreading to other stars. Maybe the existential threat will provide the motivation that pure curiosity does not. It is a grim reason to go, but it might be the one that actually drives us. Now let us consider the ethical dimensions. Is it right to send people on a journey this dangerous? Even with volunteers who understand the risks, are we as a society obligated to ensure their safety to a reasonable degree? What level of risk is acceptable? On Earth, we have regulations for dangerous jobs. Miners, firefighters, astronauts all work in hazardous environments. But there are safety standards, backup systems, rescue protocols. For an interstellar mission, rescue is impossible. Once the spacecraft leaves the solar system, they are on their own. If something goes wrong, it is over. No one can help them. Is it ethical to put people in that situation? Some would argue yes. People take risks all the time. Mountaineers climb Everest. knowing they might not return. Test pilots fly experimental aircraft. Explorers venture into remote wilderness. As long as the risks are explained and the volunteers consent, it is their choice. Others would say no. We have a moral obligation to protect people, even from their own risky decisions. Sending someone on a journey with a high probability they will not return, even if they volunteer, is ethically questionable. There is no easy answer. It depends on your values, your view of individual autonomy versus collective responsibility. Then there is the question of what we owe to any life we might find. If Proxima Centauri b has microbial life, or had it in the past, do we have a right to land there and potentially contaminate it with Earth microbes? We have already grappled with this in our own solar system. Planetary protection protocols are designed to prevent Earth life from hitching a ride on our spacecraft and contaminating Mars or Europa or other worlds where life might exist. We sterilize spacecraft, use clean rooms, follow strict procedures. For an interstellar mission, the stakes are even higher. If we find a world with life, even simple life, it is a scientific treasure. Contaminating it with Earth organisms could compromise our ability to study it, to determine if it arose independently or shares a common origin with Earth life. We would need even stricter protocols. Maybe the crew would not be allowed to land at all, only robotic probes that have been thoroughly sterilized. Or maybe we decide that the potential for contamination is worth the risk, that the value of human exploration outweighs the risk to alien microbes. Again, there is no universally right answer. It is a decision future generations will have to make, balancing scientific integrity, human curiosity, and ethical responsibility. And then there is the question of what we would do if we found intelligent life. The probability is low. Most estimates suggest intelligent, technologically advanced civilizations are extremely rare. But if we did encounter one, what then? First contact would be the most significant event in human history. It would change everything. Our understanding of ourselves, our place in the universe, our religions, our philosophies, all of it would be challenged. The Alpha Centauri crew would be humanity's representatives. The decisions they make, the messages they send, could shape our relationship with this alien civilization for centuries. Do they attempt communication? What do they say? Do they reveal Earth's location? That could be dangerous if the aliens are hostile or expansionist. Do they try to learn the aliens' language, their culture, their technology? Or do they observe from a distance, gathering data but not making direct contact? These are decisions that should ideally be made by all of humanity collectively. But with a 4-year communication delay each way, there is no time for a global debate. The crew would have to decide in the moment, based on their training, their judgment, and their conscience. That is a terrifying responsibility. The stakes could not be higher. A wrong move could start a war, provoke an invasion, or squander a unique opportunity for cooperation and learning. And even if the encounter is peaceful, there are complications. If the aliens have advanced technology far beyond ours, should we try to acquire it? Learning their technology could leapfrog our own development, solving problems that might take us centuries to solve on our own, but it could also make us dependent on them, or reveal information they do not want to share, creating conflict. And if we learn their technology, do we share it with Earth? Or do we keep it at Alpha Centauri, creating a technological imbalance between the colony and Earth? That could lead to political tensions, resentment, even conflict between Earth and its first interstellar colony. These are scenarios that seem like science fiction, but if we are seriously planning interstellar missions, we need to think about them. We need protocols, guidelines, decision-making frameworks. We cannot just send people into the unknown and hope they figure it out. Of course, the most likely scenario is that we find nothing. No life, no intelligence, no alien civilizations, just empty worlds orbiting distant stars. That is what most of our solar system is. Barren rock, ice, and gas. There is no reason to think the rest of the galaxy is any different. But even finding nothing has value. It tells us something about the universe. It suggests that life is rare, that Earth is special, that we have a unique responsibility to preserve and protect the life we have. And it means that as we spread to other stars, we are not displacing anyone. We are filling an empty niche, bringing life to worlds that have never known it. That is its own kind of significance. Let us return to the human experience one more time. Imagine you are part of the crew. 10 years into the journey, you have adjusted to life on the spacecraft. The initial excitement has faded. The routines are familiar, almost comforting. You know every corridor, every room, every face. You have had your share of conflicts and reconciliations. You have formed close friendships, maybe a romantic relationship. You have found ways to occupy your time. Hobbies, studies, work. But there are moments, quiet moments, when you are alone. When the weight of what you have done hits you. You are never going home. Earth is a point of light behind you, indistinguishable from any other star. Everyone you knew, everyone you loved, they are all gone. Not dead, not yet, but gone from your life. Moving forward through time without you, you will never see them again. You will never walk on Earth again. Never feel rain, never smell fresh air, never see a tree or hear a bird. All of that is behind you, irretrievably lost. And ahead of you is only more of the same. More corridors, more recycled air, more of the same faces for decades. And then, if you are lucky, you will arrive at a world that might be hostile, barren, nothing like Earth. In those moments, you might question your decision. You might feel regret, sorrow, even despair. Why did you volunteer? What were you thinking? Was it worth it? But then you remember. You remember the reasons you went, the curiosity, the adventure, the desire to be part of something larger than yourself. You remember that you are doing something no one has ever done before. You are traveling to another star. You are expanding the boundaries of human experience. You are part of history. And you find meaning in that. You push the doubt away and focus on the mission, on the goal. You are not just surviving the journey. You are contributing to humanity's future. Every day you spend on this ship, every problem you solve, every piece of data you collect, it is all part of the mission. It all matters. And that gives you purpose. That gets you through the hard moments. The crew would develop rituals, traditions, ways of marking time and creating meaning. Anniversaries of the launch, birthdays, both Earth birthdays and ship birthdays, the day you boarded, holidays from Earth cultures, celebrated and adapted to the spacecraft environment. Maybe new holidays invented just for the crew. Naming days for children born on the ship, remembrance ceremonies for those who pass along the way. These rituals would help create a sense of community, a shared culture that binds the crew together. And they would tell stories. Stories of Earth passed down to younger crew members who have never seen it. Stories of the launch, the training, the early days of the mission. Stories invented on the ship, myths and legends that reflect the crew's experiences. Over time, these stories would become the foundation of a unique culture. Neither fully Earth nor fully something else, but a blend. A new identity forged in the crucible of interstellar space. By the time the crew reaches Alpha Centauri, they might not think of themselves as Earthlings anymore. They might be something new, star travelers, pioneers, the first of a new branch of humanity. And that transformation, that evolution of identity, is part of what makes the journey terrifying. You are not just traveling through space, you are traveling away from who you were, toward who you will become. And you do not know what that will be until you get there. Now, as we finally approach the end of our journey tonight, let us take a step back and look at the big picture. The journey to Alpha Centauri is more than a technical challenge. It is a test of everything we are as a species. Our ingenuity, our courage, our ability to work together toward a common goal. It is a statement about our values, about what we think is important, about what we are willing to sacrifice for knowledge and exploration. And it is a gamble, a bet that the universe is worth exploring. That what we will find out there, whether it is life, resources, knowledge, or simply the achievement itself, is worth the cost in time, money, and human lives. We do not know if that bet will pay off. We will not know until we go. But the very act of making the bet, of committing to such an audacious goal, says something profound about us. It says we are not content to stay in one place. We are not satisfied with the familiar and the safe. We need to push boundaries, to see what is beyond the horizon. even if the horizon is 4 light-years away. That drive, that restlessness, that curiosity, it is what makes us human. It is what drove our ancestors out of Africa to populate every continent on Earth. It is what drove us to cross oceans, to climb mountains, to explore the poles, to land on the moon. And it is what will drive us to the stars. The journey to Alpha Centauri is terrifying, but it is also inevitable. Someday, someone will make that journey. And when they do, they will carry with them the hopes and dreams of all of us who looked up at the stars and wondered. Thank you for joining me tonight on this deep exploration of what it would really take to reach Alpha Centauri, our nearest stellar neighbor. We have looked at the distances, the technologies, the human challenges, the risks, the potential rewards, and the philosophical questions that such a journey raises. If this exploration moved you, challenged you, or made you think differently about humanity's future in space, please take a moment to like this video and subscribe to the channel. Your support helps me continue making these deep dives into the cosmos and our place in it. And remember, the next time you look up at the night sky, if you are in the southern hemisphere, you can see Alpha Centauri, a bright point of light, deceptively peaceful, hiding the immense challenge it represents. 4.24 light-years away, 25 trillion miles of empty, hostile space, a journey that would test the limits of our technology, our endurance, and our humanity. A journey that is terrifying in its scope, its dangers, and its implications. But also a journey that is calling to us, beckoning us forward, daring us to take that next great step. Sleep well tonight, knowing that somewhere in the cosmos, perhaps sooner than we think, that journey will begin. And when it does, it will mark the moment when humanity truly became an interstellar species. Good night, and may your dreams reach for the stars.